This is the first problem from Chapter 8 on electric force and electric fields. And it says, the nucleus of the helium atom contains two protons that are separated by about 3.0 times 10 to the negative 15 meters. Find the magnitude of the electrostatic force that each proton exerts on the other. And in parentheses, the protons remain together in the nucleus because the repulsive electrostatic force is balanced by an attractive force called the strong nuclear force. Okay, so here are the couple of protons. The ones in red here, and then there are a couple of neutrons. A typical helium atom contains two protons and two neutrons. It's possible for it to contain a third neutron or just one, but it always has to have two protons, and that defines it as helium. In any case, this would be the distance they're asking about between the middle of the protons. Of course, the whole thing is a model anyway. This is how we envision. Okay, I don't know how this happened here. How we envision how the nucleus looks inside. We make kind of balls or spheres and go from there. And this is, of course, the separation distance they were talking about. I'm trying to figure out my own tablet here, and it kind of tries to play tricks on me again. Boy. So here's the separation distance, d equals, let's see what that was again, 3.0 times 10 to the negative 15 meters. And they're asking for what the force is, and really the only thing we can use here is Coulomb's force, which says that the force equals the constant K times fraction bar charge 1 times charge 2 divide by, and here I have to look if they use D for distance in our book, if they use R for radius, and they usually use R for radius. And after that, it is just a matter of plugging in numbers. I think I need a lot of space here. So where it says D right here, well, that becomes my R over here. I just said D for distance, but Coulomb's law writes R for radius or distance. So plug in the numbers here, 8.99 times 10 to the 9th. And as I said, I'm trying to figure this out. Come on. And the units are really interesting for the constant. In fact, I think I'll show them in just a moment. This is not correct yet, but I'll fix it in a moment because I want to show something there. Times, well, the charge of one proton, look it up in the book. Top of my head, 1.67, right? Yep. Nope, that's the mass. Sorry about that. Where'd it go? I ought to have it memorized. Oh, 1.602, of course. I do have it memorized. 1.602 times 10 to the negative 19 coulombs. Again, I'm trying to it keeps playing tricks on me. Come on, just give me the 19 there. There we go. Coulombs times, well, the charge of the other proton, but that happens to be the same. So I'm going to shorten this here. I'm just going to make parentheses around it, and I say that's squared. Same deal. Divide by the distance squared, which is given here in this problem as 3.0 times 10 to the negative 15 meters, and that one as well squared. Okay, back to the unit for the proportionality constant K, and I actually don't have it memorized, that unit, because it is so strange, but it's easily to be figured out the force has to come out as newtons. That's why I already wrote the newtons here. And then the Coulomb squared have to divide out somehow. So that unit, that constant, incorporates Coulomb squared. And the meter squared have to divide out. So that's why the unit looks that way, so that the coulombs are gone, the meters are gone, and the only thing that remains are the newtons. And then I'm going to put my little underlining bar here, and I'm going to do newtons here, and of course that is for you to calculate how much that is going to be. Top of my head, if I look at that here, -19 and there's a -15, so if you use the law of exponents, then it's -4, but that needs to be squared, which is -8, and then with the 9 here it's 1. 9 minus 8 is 1, and so 10 to the first, so roughly in the neighborhood of like 10 newtons or so. Well, actually a little bit more, like 40 to 50 newtons perhaps, in that neighborhood, somewhere around there. I didn't do the calculation, you do the calculation. But actually appreciable. That's in the neighborhood of maybe 10 pounds or so. And between these tiny, tiny protons, and of course the reason is because these are really, really close together. Again, my thing here about 40 to 50 newtons was kind of ballpark figure. Maybe it's a little bit less, maybe it's a little bit more. You will calculate it. Okay, I just pulled this one up here on hyperphysics. It says in the parentheses, well, as the electrostatic force tries to push them apart in that neighborhood of about 10 pounds or so, well, there has to be another force that holds them together, and that's called a strong nuclear force, which has to be at least that much. So huge forces are acting inside the nucleus. And this is just a description of it. It's kind of hard to understand. There's a strong nuclear force, and in the end, you just have to accept that there is, because otherwise things would be flying apart, and all we would have in the universe would be hydrogen atoms, and we don't. So there must be a strong nuclear force holding together. Here they try to explain it with that, or they do explain it with that these little particles called gluons are holding the protons and neutrons together that are being exchanged between the quarks inside the protons and neutrons. Anyway, that's just a little bit on top of what this problem was about. Okay, the next problem is, except I lost my space in my book because all of a sudden I couldn't remember the electric charge of the proton, which I have memorized for past 30 years as 1.602 times 10 to the negative 19. Anyway, new problem. It says a small spherical insulator of mass 8.00 times 10 to the negative 2 kilograms and charge plus 0.600 microcoulombs is hung by a thin wire of negligible mass. A charge of negative 0.900 microcoulombs is held 0.150 meters away from the sphere and directly to the right of it. So the wire makes an angle theta with the vertical. See the drawing. Find A, the angle theta, and B, the tension in the wire. This will become kind of involved. In fact, the problem has a double start on it. Okay, let's see what is happening here. For one thing, they want to figure out what the tension is in the wire. So what I'm going to do is, give me one moment, I'm trying to find, I think I'm going to use blue as a color. Okay, that arrow that I just put there on the very right, I just wanted to get it back on the page. So there's the tension that we're supposed to figure out. And I guess I'll label it as such. So there's the tension. But then we have to see what kind of other forces are working on here. Obviously the electrostatic force. So there's going to be Fc between these. And notice that I write these as vectors, which makes sense because they're pointing in certain directions, so that's important. So that Fc is this way here, and I wish that would be blue like I had it earlier. Oh boy. There we go. I'm going to click there, and will I get an automatic blue one this time? No, I don't. Okay. There is a third force here, and because it's hanging from a wire, it must be its own weight, so gravity pulling it down. There we go. So Fw, and actually, about that T that I wrote there, I'm going to take that back. Actually, I would like to write an Ft. I just noticed I do prefer to write a force as a capital F and then put indices around it. Oh, underneath, I mean. Okay, so tension, Coulomb force, and the weight. So when I add all these forces, and you could tell me what that very, very important law is that I'm using right now, respectively, because I'm recording this to myself, you cannot tell me. So obviously this is Newton's second law, where forces are added, and because everything is in equilibrium, nothing changes its motion. In fact, it's still anyway. The acceleration comes out to zero, so the net force is also zero. And that's the equation we have to solve in order to figure out what they want us to figure out. Looks easy enough, right? But we're dealing with vectors, so we have to deal with components, so x and y components, so it's actually two equations. Okay, here's the x component. And what I have in the x is the tension times cosine, and I'm going to call this alpha because if you took the previous class from me, then you may recall that I like to have the angle measured from the positive horizontal, and the reason is that way I can always use the cosine with the horizontal and the sine always with the vertical. Okay, and then later on we'll figure out how alpha actually relates to theta, but the outcome will be just fine. We get the right result. In a vertical, we have a tension of Ft times sine alpha, and again, that's the reason why I use that. I don't know why this keeps popping up here. Somehow I still have to figure out my tablet. So times sine alpha, because it's the vertical, and now the Coulomb force that acts only in the horizontal, so Fc, and then I'm going to have in the vertical the Coulomb force is 0 because it has no vertical component in this problem, and then the weight, which is 0 in the horizontal, obviously, and that equals 0 because the net force is 0. And in the vertical, it's the weight, that is m times g, times the sine of, and look at this one here, 270 degrees, right? Measured from the positive horizontal, it's 270 degrees. That's why we're getting a negative in there. And